I still haven't decided yet. I might not even include chapter 1 question. I might not pull a question from chapter 1. Because if you look at back on chapter 1, we've been doing chapter 1 for every exam. Right? So I might not even include it. It might be, sorry, not chapter 1, exam 1. I might not include anything from exam 1. Exam 1 might be replaced by a problem we go over today. So I haven't decided. But yes, the problems will be pulled from your exams. And whatever we cover today will be not, it won't be like a rigorous hard problem I'll put on these finals. It'll be more just like concepts. But by default, I think you understand now that a lot of my problems are a little bit more on the difficult side. Except for when they're easy, right? But sometimes they're just up to easy, so. Okay. So, my lecture today on fluids is a little bit loose. So, I kind of, because it's a material science, and it's empirical in a lot of cases. So, fluid, what is a fluid? Oh, did any of you need to go over anything from the quiz? Or did everyone get it? I think everyone got it. I looked at it this morning. Everyone did good. So for that last problem, right? Always start with momentum, right? When I did the problem prior, I did conservation of angular momentum. Angular momentum is a derivative of regular momentum, right? So if you just start with momentum, I wish this book was written differently, where we start with just momentum, we derive forces, and then we use dot products and curls to derive the different types of forces. That's how I would have done it. But that requires you know a little bit of math, right? And in hindsight, maybe you know that math now, but if I were to just start out at the beginning of that math, it might have been a little bit harder. So just keep that in mind, that a lot of this stuff is still the third exam, it will be one like the baton problem. So you're going to have to go through, it's not going to be a baton, it might be a water molecule, it might be something, right? And what's going to happen is that thing's rotating and it's going to break apart. And when it breaks apart, you're going to need to figure out how fast the thing is rotating at the end, okay? So pick your favorite structure, make up your own structure. In fact, we can do it, if you want to do it a little how I study. Yeah. So let's do a little example. Let's say you have some molecule, I don't know what molecule that is, but it has some structure. Or maybe it's like, right? And some reaction happens, and it breaks off, and it becomes something like, in fact, I'm not even going to write C, I'm just going to write. So let's say these are M1, M2, M2, M1, 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 and then this is M1, M2, M1, M1, and then this would be M2, M1, M1. Say it flies off this direction, V, and this flies off. Actually, this would be a good trick question. Okay, so this molecule flies off this direction. What direction should this molecule fly off of? There's nothing happening here, it's just spinning. So it's just spinning here. So V is 0, omega is not 0, right? And then here, omega, let's say, this is where you have to kind of put your own imagination into it, right? So we could say omega here is equal to, I don't know, 5 radians per second. It's your choice, you know, you're the one that decides. So let's call this molecule 1, and then this will be molecule 2, and it's rotating at that speed, right? And we want to know this one. We want to know how fast this is rotating. We know how fast this one's rotating, it's given. And then let's say this flies off at 500, now let's do, 500 meters per second. I forgot how fast air was. Do you remember when we did an example at the beginning of class, or beginning of, way back? Was it like 300 or was it 500? I think it was 500. Doesn't matter, 500, we're just messing around. So assuming, I'm not gonna go through this, but you should know how to find I for this, right? I1, follow this. I2, you should know how to find it. Okay. This one's easy because everything is symmetric. So let's say that these are all symmetric. Right. And if this distance is L, so let's call this L. Let's keep these L. Let's say L. And I'm gonna get rid of this double bond. Double bonds are shorter, right? So to keep them equal, let's just say they're L. Okay? So anyways, the point is, back to my question, what direction should this molecule fly to? If I'm flying this direction, what's the other direction? Yeah, it has to be, right? Because total momentum here, P initial is equal to P final. And initial, it's 0, right? And final, it's whatever this molecule. Let's call this capital M1 and capital M2. Right? So capital M1 flies off at V1. Let's call this V1. Let's call this V2. And then second molecule flies off on that speed, right? From this, if you're given the masses, if M1 is known and M2 is known, right, we can actually determine the final speed. So M1 and M2, right? So its initial momentum 0, it's just spinning. So K initial, K rotation initial is not 0, right? Afterwards, this molecule flies off in this direction at 500 meters per second. This molecule flies off in this direction, right? So if you know M1 and M2, right, you can find V2. So V2 equals M1, V1, divided by M2 minus. Because it's going in the opposite direction of V1. Now notice, even though it's minus, does the minus tell me, for example, the negative here is just saying I'm moving opposite V1, right? I didn't specify a coordinate system here. Have you noticed that? I said nothing about the coordinate system. I may have said this is positive rotation, right? So far I haven't said anything else. This is pure fundamentals. Okay, so now we know both speeds. Now we know both speeds. Let's say our initial omega, I omega, is equal to, I don't know, let's say 10 radians per second. Right? So I just said here was not equal to 0, but now I'm going to give it a value because now I want to know something. I want to know, right, what's this rotation, okay? If I don't know my initial speed or my initial rotation, I will not know my initial energy. If I do not know my initial energy, I do not know how to calculate or add up the energy of this moving this way, the energy moving this way, and the energy of this rotating, and the energy of this rotating, right? So, always, what we did first was use momentum laws. Now 2, what is the next thing we gotta do? What's after momentum? You're gonna have to know this for
Energy.
all the problems you ever encounter
Energy.
going on. Yes, energy. Okay. Momentum's always true. I will keep repeating this forever. This is always true, no matter what. It is always true. The only time I think that this might actually break down is if you go into systems that fold in on themselves, not an astronomer, but like twisting black holes, they kind of fold space in on itself. And so you could get a situation where you see yourself going one direction and you're actually traveling the other direction, in which case your momentums are not adding up correctly, right? Okay, so how do we find omega 2? Well, we know our initial K rotation, right? And that is just our initial energy. We don't have energy anywhere else, right? It's rotating. This is our initial state. It's rotating. Okay, so that's all we know. And our final state is the momentum 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 I1 omega 1 squared plus 1/2 I2 omega 2 squared equals 1/2 I initial omega squared initial. Okay? So that's how you do this problem. Now you just solve for omega 2, right? So you just subtract this over, subtract this over, subtract this over, multiply by 2. In fact, you can get rid of all your 1/2s, right? And it just becomes these things subtracted divided by I2. Right? And then that's how you do it. Yes. So how I labeled it is how it is. So omega I, so this will be I. It's very hard to keep your labels consistent if you haven't been doing it for a while, but I highly. So this is how you create a problem for yourself. Just make it up. And then remember the rules. And then plug things in and see if they make sense. Yes, the equilibrium problem. I recommend studying the crane problem. The crane problem. The crane problem? Crane? Crane?
Oh, I thought you were like saying
crane problem. Okay, fluids. What are fluids?
what were we talking
Chapter 11, I think. It's in your homework. It's in your homework, alright? Say your homework, chapter 11. Do your homework. What are fluids? 1. Fluids take the shape of any object. It contains any object that contains it. 2. The what happened to? I think that's it. Oh yeah. Fluids all carry the same density given a volume. All fluids of the same type. So if you have a small cup of water or you have a large cup of water, the density of water is the same, basically, is what that means. Right? So density, what is density? Density, as we all know, is the mass divided by the volume. Why is a small cup of water density not the same as a large cup of water? Why are these two densities the same?
They're the same.
Yeah, they're the same, but physically, why are they the same?
Because when you go from a smaller cup to a larger cup, the mass increases with the volume.
Right, right. You could also think of this as a counting unit, okay? So let's just take water, for example. If you have H2O, right? So if you had one water molecule occupying some volume, right? And then you add another water molecule occupying more volume. The only way to occupy more volume is for you to increase the volume such that it can contain two more, right? And you can't really alter the masses. So the masses go proportional with one another. You increase the volume, you increase the mass by just the same amount. And as a result, if you have, what screws this up is if you have like some salt. You have some Na, so you have NaCl. When you start adding things like salt, it changes the mass, right? So you have more mass here for the same volume, and so this would not equal this, so the densities will not be equal. So the density of salt is a little bit more than the density of water. Or density of salt, sorry. And you can go to critical saturation. So like if you have enough of these molecules bouncing around, they want to reduce down into a more stable state. So what will happen is you can't expand anymore. Let's say your volume is nominal. Volume is constant. You can't expand anymore, but you keep adding more and more salt. So what happens is these NaCl get too close to where the energy forcing them together is enough to cause them to bond. And then you start forming salt crystals. And this is called critical saturation. Sorry. So this, when you start forming these structures, critical saturation. Well, that's just structure of salt, the cubic lattice. It's different for other molecules. For example, you're growing sugar crystals. Sugar is a way more complicated structure, and I don't even know if they're exactly crystals. I guess they are organic crystals. But yeah. So specific gravity. So we have density and specific gravity. Specific gravity has nothing to do with gravity. Has nothing to do with gravity. It is basically the ratio, it's the relative density. So they really should have just called this relative density. It's the relative density, so this is relative density to water. Okay. So let's say you have some density, you divide that by the density of water, and this is your, I forget what symbol they use for this. I think they use C sometimes. This is specific gravity. And what's the density of water? Yep, it's 1 kilogram or 1 gram per centimeter squared, or cube, sorry. I don't know. So depending on what your units are, you'll have to convert this to grams per centimeter squared, or you can convert this to kilograms per meter cubed, either one. And to give you some examples, for example, relative density, so density of iron, right? So density of iron is 7.8 times 10 to the 3. I believe this is kilograms per meter cubed. And if you divide that by the density of water, you see 7.8. Right? Okay. Does that make sense? No, because you have unit density divided out, so it's units. Yeah. It's just a ratio of how much heavier the object is compared to water. So iron is 7.8 times more dense than water. That's how you can kind of read the specific gravity. Water is very unique though. Water, there are two types of fluids. Well, not two types, but there's two mechanical uses. There's compressible fluids and incompressible. We will only be focusing on this. We will not focus on compressible fluids because compressible fluids is, it gets more complicated because when you compress something, what does it want to do? Yeah, so it wants to uncompress. So there's a repulsion force, right? And if you remember from this whole problem, you push on something, right, it wants to push back. And so compressible fluids are often used in systems that have an oscillation. So like a gear grease is compressible. But anyways, water is incompressible. Why is water incompressible? Or close to incompressible? I believe it has like 0.998 compressibility or something. It's like really incompressible.
Does it start evaporating?
What was that?
Does it start evaporating or
Okay, let's say it can't evaporate. It's closed and you're trying to compress it. Why can't it compress it? It's a more a physical reason, but you could say that everything interlinks. So if you look at water, you can cross-link this small water molecule like this. Right? You can also then put this molecule here, put this molecule here, this molecule. Here. So you can just play this game and try to fit as many things together. They kind of fit together very nicely like link balls. But what is in between these molecules? What is in between the molecules of the water in this bottle? Besides, I don't know, bacteria and whatever. If it was a perfect glass of water, right, this would be vacuum. So if there's nothing else in the bottle, there is literally vacuum between each water molecule. And because the molecule, let's say this was, so this is oxygen, right? So this is hydrogen. So this is oxygen, hydrogen. If I were to exert a force here, right? So F, and we're to kind of push on this thing, creating a pressure, these two molecules would then be forced against one another, right? In fact, all these molecules would be forced against one another. So this is positive, right? This is positive, this is positive. These two would be forced against one another. And if you try to force these two together, the interaction So the force of interaction is roughly this. Here where R is the distance between them, right? And then this distance is usually on the order of an angstrom to an nanometer, right? So an angstrom is roughly 10 to the minus 10. A nanometer, 10 to the minus 10. So you can imagine this force is really, really, really strong the closer these things get. And as a result, it's incompressible. It becomes too much, too strong, too strong. And as a result, you have an equal and opposite exchange, right? We're in a vacuum, remember? So this molecule acts on this, so let's call this 1 and 2. This is F1 on 2, and then this is F2 on 1, right? So you can keep doing this, right? You can have this be like F2 on 3, and this is, I don't know, F3 on 2. And if you keep doing this, right? So we have F1, 2 plus F2, 1 equals 0. F2, 3 plus F3, 2 equals 0. And you just keep playing this game, and what you'll find is everything is 0 inside. And we went over this already. What is this called? What law is this? What law does this come from? Everything is added up to 0. Remember when we did forces on a system? The total forces on a system can be the sum of the internal forces plus the sum of the external forces. And we found that when we do the internal forces, it's this. It's the sum of a bunch of zeros. So this internal is 0. Right? And so the only force left is this external force that you are exerting. And so it has to appear out on this side. So you can have, so with incompressible fluids, so incompressible fluids, transmit forces perfectly. This is a mechanical advantage. Mechanical advantage. For hydraulics. I kind of went over this 2 classes ago or something, where we're doing mechanical advantages. I brought up the point that you could have a mechanical advantage from this. So that mechanical advantage comes about when you talk about areas and weights. So let's say you have some mass here, some smaller mass here, some area 1, area 2. The pressure here needs to be the same as the pressure here, if this is water. So if we look at this, M1 over G divided by A is your charge per area on this side, so A1. And M2 divided by G or A2 is your force on this side. And if you were to solve for this, you can get a very, very small force resulting on this side from a very large force on this side and vice versa. So by applying this small mass, you're able to lift this big mass, basically, is the idea. And this is scalable, sorry, this is a 1. This is scalable based on the area. So as long as you have a small A1 and a large A2, the amount of force needed to lift this big mass is always going to be small. Right? So this is called a hydraulic lift. It's the same thing they used to lift cars. Okay, so let's talk about water in a cup. So you have a cup. You have a piece of water. And I want to add up all the forces on this piece of water. Right? So we have the force from things above. We have the weight of the water. We have the water pushing on the sides. Right? And then water pushing on that side, and water pushing on that side. Why is water pushing on this water piece? Because of this. Internal forces, right? They all push on one another. We're looking at the forces pushing on this water piece, right? Okay? So we need to, let's see, what did I do here? We need the volume, right? We need the volume, we need the mass, and from that we can get the weights. And then we can just add the sum of forces in different directions. Okay, I see. So let's just look at the y direction. Y half direction. So first of all, let's just say dV is equal to the area times dz, right? So let's call this dz, and then let's call this area A, right? And then dm is equal to rho dv, which is equal to rho A dv. So that means dW is equal to dm, g equals rho g A dv. So here I just replaced y with z because it would be the same. Alright, so the sum of forces. Sum of forces from the bottom, so we have things acting on the bottom, which is rho times A, minus forces from the top, so we have a change in pressure. So let's call this pressure P. As we move up, we have P plus dP, right? And so this is, rho plus dP times K. And then we have minus the weight, rho G A dy. So it just changes dy. And that equals 0. And then we can just solve, right? So really, what are we solving for? We're solving for a change of density of water as a function of its height. Okay? So let's multiply this through. Sorry, I don't know why I wrote rho. This is P. Yeah. So the pressure down here is going to be at some value. As you go up, you have a change in pressure. This change in pressure can be positive or negative. Right? So we have PA minus PA plus DA minus rho GA dy equals 0. have the change pressure, rho A, rho G A. These cancel with rho. And then you can take this integral, right? So if you take this integral, you get the change in pressure equal to rho G delta Y. Assuming constant flow.
That makes sense.
Okay. So we can use this equation to find certain things. Time is it? 30%. Sure. How many of you know what a barometer is? A manometer? Well, yeah, it checks pressure. It can check actual. So what's the difference between air and water? Is air a fluid? It's a gas, right? So what's the difference though?
What is it? Water can't be water.
Well, if there's water in this water, it's not just weighing the water.
So gas is actually can be modeled as a fluid. If you go into space exploration and all that stuff, they usually model gas clouds as fluids. And it depends on scale. The bigger the gas cloud, the heavier the gas cloud, the more the gas cloud behaves like a fluid. But in all intents and purposes, they are very different. In fact, you have steam, which you could say is kind of a gas. And you have water, which is a liquid. Gas is a change of state, but keep in mind you can still use the same equations to describe it. What changes is the assumption. So anyway, back to the original question. What is a barometer? It is the most useful and simple tool that you could ever encounter. It is so simple, it is still used to this day in every machine that you'll ever work with. Every machine will have a barometer, a manometer, of those types. And it's basically, so let's say this goes to your chamber. So you're working with, let's say, a plasma machine or whatever, some sort of machine. This goes to your chamber, it has some pressure P. And then inside here is some liquid, usually water or mercury. Well, old days it was mercury, but usually it's just water. And then outside you have another pressure P. So let's call this P atmosphere. So it's in the atmosphere. And I want to know what the pressure is, or the difference. I want to measure this pressure given some change in height. So I have H. And then you can have this be, let's call this Y1. And this is Y2. And how we do this is we just equate the pressures through the fluid, right? So here we have rho plus GY1. So that's the pressure here, pressure. But that pressure needs to be equal to this here, which is just P atmosphere plus rho GY2, right? So all I did was I used this equation, right? Change in height, I have my pressure, okay? And then here, change in height, then my pressure. And these need to be equal, right? So these are equal to the same pressure, P. That was P1. Right? Because at this level they should be the same pressure, right? So So at this level, they should be the same pressure. We equate these, we have P1 plus rho gy1 equals E atmosphere plus rho gy2. And we have P1 as P atmosphere is equal to rho dy2 as y1, which is a rho d. So you read off the height, you multiply it by the density of water times density of gravity, and then that's how you have the change in pressure from atmosphere to your chamber. So this would be like some nozzle sitting open on the outside of your chamber, and then you just look at this height, and then from that you can tell the pressure of your inside chamber. It is used all the time. There are different types. It's called a gauge in general. In general, it's a gauge, right? There are different types of gauges. Alright. Any questions on that? Okay. Buoyancy.
Quick question, how many questions can be on the exam?
Which one?
How many questions?
Oh, which one? Which is it? Is that 3? Probably 4. Yeah. I told you everything already. I think I already told you.
Like written 75.
Did you already know? Okay, buoyancy. We'll talk about it later, but I think I said enough on that. Okay.
Fantastic.
I have a long paragraph for how to describe this, but I want to try to talk about it in a simpler way.
Buoyancy. Yancy.
I don't know how to
Yancy
say this any other way, so I'm just going to write it out. Buoyancy. When a body is completely or partially immersed in a fluid, as though fluid exerts an upward force on the body equal to the mass, equal to the weight of the water displaced. So I have, let's say, a boat. It takes up some surface of the water. The weight of this water, so weight of water displaced, is the upward force. So it's not the normal force like how you would have it in a normal system. You have a buoyancy force, so I'll just write it as B, and then you have your weight, W. Right? So for something like a boat, you would have I think I actually use real values here. So let's say we have a boat of mass 6.1 times 10 to the 7 kilograms, and a height, so it sinks at a depth of 10 meters, so h equals 10 meters, and then it's wide about, how wide is it?
You might use it.
Or maybe that's what I'm solving
This.
for.
Or the bridge. This is
Yeah, I want to find D. I want to know how wide I need to make my boat if my boat sinks 10 meters deep, right? So all we do here is the sum of forces. So F, B, minus W equals 0. And then B is equal to the weight of the water, right? That's by this buoyancy rule here. B is the weight of the water. And then rho times salt water. So salt water is what is it? It's slightly more dense, 1.03 times 10 to the 3 kilograms per meter. So it's about 30 kilograms more dense than actual water. So density of water times the volume displaced, so this is V, so V, right? And we can actually say that V is this height times this distance times this length, a length of the boat. And what, did I put a length for the boat?
Yes.
Oh yeah, length of the boat is equal to 300 meters. Okay, so that's the length of the boat. G equals mg. And this is the weight of the seawater. This is the seawater. So, if VDHL is equal to DVHL, give me 1957. Oh yeah, and V, so V is equal to mass of boat divided by salt water, give me about 59223.3 meters. So here I just solved for B. I solved for B here. See that? I just divide these over. Divide G here, divide rho here, and I get B is equal to this value. And then I use this here, the volume I wrote here. If this is this, then I can solve for D. And this is the length, or this is how wide the boat should be.
That's distance. Yeah.
How wide. I will likely include a problem like this. It's simple, right? It's just buoyancy minus weight, and then you solve. For the final, I'm going to include that. Okay. Any questions on this? I guess I have my own question. Why is this true? What's the physical reason for this? Anyone think of one? I was actually trying to think of one because I didn't really think about it last time. I kind of just took it as a principle. But if I were had to guess, it's because okay. It's because of the weight right, so if we look back at this picture, this piece of water here is experiencing the force of the whole thing on it, right? And for it to stay still, it has to satisfy this equation, right? So, if you were to remove it from this, so if you were to remove the water, the equation would still be the same. You would still have the same amount of forces acting on that body because we're only looking at the forces of the body, right? Of the water on the body. Water on body. And as a result, equal and opposite, right? So if the weight of the water is what's exerting on the cup of the water, then the opposite reaction would be the cup exerting its own opposite force of the weight to keep the water there. And as a result, if you were to replace it with anything else, it would just exert the same amount of force that it would exert on a piece of water. But that's my explanation. You can think of that one. I'm all yours. I don't know about ask a question. This is more for you. This is more for you to understand that there's mechanical advantages built into everything. So. Okay, fluid flow. Fluid flow is a little. I don't know how I'm going to derive this. I don't know if I should take it technical or should be a little practical. I think I'll make it practical. Fluid flow. So suppose you had a tube and it goes along and it gets smaller, it becomes a smaller tube. We want to look at how the fluid flow goes through this tube. Okay, so this will have area A1, it will have a pressure P1, it'll be at some height Y1. So this is an actual height, so there's some change in height. So this tube goes from some lower altitude to some higher altitude. Alright. And then somewhere up here you have V2, P2, and then you have A2. Okay, so the cross-sectional area, the pressure in this region, the pressure in that region. And V2 is actually the velocity, the velocity here. V1. Here they usually just use speed, so I'm probably going to just use speed as well. It's really hard to talk about the direction of the fluid because it's just really, it goes in the direction that you want it. Okay, so what is the volume dV1? Well, it's an area, right? It's A1, this area, times whatever this small displacement is. So this piece moves from here to here, and let's call this ds. And so, because it's not compressible, right? If I push it, then this thing, it can't compress, so the other part has to move forward as well. So this over here moves a distance ds as well, right? So dv1 is ds, and then dv2, a2, ds. I'm going to label these different for now, just to be general. I wanted, okay, so if this wasn't water, what would happen? Would ds1 and ds2 be equal?
No.
Yeah, exactly. It wouldn't be. So if it's oil or whatever through a tube, it probably won't be equal. So for generality, we'll just keep it general. And I want to convert this to actual mass, right? So how do I convert this equation into a mass equation?
Area.
What do I multiply by? No, we already have volume. What do I multiply this by to get a mass? What do I multiply volume by to get a mass?
Density.
Yeah, density. So we have density equal rho EV1 equals rho A1 DS1. But this is equal to the mass M1, right? And then if we do the same thing here, we have M2 is equal to rho dV2 A2 DS2. But if we're dealing with an incompressible fluid, remember what I said, the space needed for the molecules to be occupied, they either need to have the same mass for molecules that are incompressible, so if you start adding stuff to it, it won't be, right? So for incompressibility, dm1 has to equal dm2, or m1 equals m2. These are actually dm. So the mass displaced at your entrance is the same as the mass leaving at the end, right? And so if we equate these, we just get rho VA A1 B. What did I do there? Oh, I didn't say this up here, but what else can we write ds in terms of? So I have V1. Can I write ds in terms of V1?
Yes.
Yeah, I can, right? So there's another expression. We can write this as A2 V1 times dt. And then this is this is A1 V1 dt. So that you can write it in terms of the velocity. And I wrote that here, but you don't really need to do that. You can just equate these two. If you equate them, you get rho ds1 is equal to, sorry, I just want to equate these two. Rho a1 ds1 is equal to rho a2 ds2.
That's the area.
The densities divide out, and then we can write ds1 and ds2 in terms of this velocity, right? So we have a1 v1 dt equals a2 ds2, sorry, v2 dt. And then your t's just cancel out, and you have a1 v1 equals a2 v2. So this is how you increase the speed. Have you ever had a hose and then you put your thumb in the hose thing and it comes out faster? That's what this is. That's this rule. You're decreasing the area. So let's say A1 is the water spout thing and it's coming out some volume. And then you're controlling A2 with your thumb, right? So A1, B1, A2, B2. If you make your A2 smaller with your thumb, this is a small number dividing a big number, so your V2 will get larger, right? So the water outside the nozzle will get faster, right? So that's basic. Units, if you look at units here, if you look at V1 is equal to meters per second squared. And if you look at area, this is meters squared. So V1 times A gives me meters cubed per second squared. Sorry, not square. Sorry. 1, and then I want to write in square. So this is volume per second, right? And in fact, you can just write it as dV dt equals VA. General volume rate. So if you know the cross-section area of a pipe and you're able to measure the output, in fact, you know what? You don't really need to measure the output. You just need to know the incoming, right? You just need to know the speed at which you turn on the nozzle. And if you know the area, and you know this, you can solve for A or B, right? And then this would just give you a constant equation for the volume flow rate. So you will have problems like what would be this problem? You might, do I have time?
Change in velocity.
Oh, we have time.
Or change in time.
Okay, are there any questions on this?
DT is changing time, right?
Yeah.
And DS is changing speed, right?
DS is displacement.
Okay.
So that's just the displacement here for this. So it moves this distance, ds.
Okay.
And then it moves this distance, ds2. Okay. Alright, I think no questions on that. Let's talk about the work. So using this expression still, so we're still in this case, we're still looking at this case, but now we want to look at the work. So dW equals F dot ds. Okay. So we want to look at the work on the fluid. That would be force, right, is just the pressure times the area, right? Pressure, area, and so the work on that little piece at the beginning would be the pressure at that area times the displacement, right, ds1, which is equal to rho 1 v1, right? And the work on the other piece is actually the opposite. Why is it the opposite? So it's negative P2. But why is it negative? Can anyone tell me? So I push on the fluid. What does the fluid want to do to me? Right, push back. So that's why it's negative. Because remember, I push the fluid, that piece displaced, and the other piece also displaced. But it displaces with a pressure pushing back on it, right? So we just do total work, right? So the total work.
Professor, the W is for weight, right? DW is weight, changing weight. What's
What was that?
the W? What does it stand for?
Oh, work.
Okay.
Yeah, it's just work. It's not weight, it's work. Alright, so this would be dW equals dW1 plus dW2, which is equal to pressure dV1 minus P2 dV2. So the total work on the system is just the change in pressure times the volume. Why are the volumes the same now? Why did I make them the same? No, I pulled out my I set V1 and V2 equal, right? And then I pulled them out. Am I allowed to do that? Is that fine?
Yes. Yes, but
Are we
then-
talking about water or anything else? It's actually fine,
Water, yeah.
because it's incompressible, right? We're talking about water. Incompressible.
So what would you do if it were compressible?
If it were compressible, you can't do that. It would just be the difference of those two. You would probably try to get it in terms of displacement, or velocity. I would go back to the velocity description in that case.
Okay.
But that's more for engineering type questions. Oh yeah, the kinetic energy. So we want to look at a piece of the kinetic energy. So 1/2 dm1 v1 squared. Oh, why am I doing everything in these little differentials?
Because water's in movement, so it changes. It's a change in something.
It's because it's so small, right? It's so tiny, and there's a reason I started out with talking about these molecules, right? So everything when you talk about fluids, you have to just think about it in terms of molecular interaction, always.
So does D stand for like really small?
Yeah, yeah. So differential dm1 and dk1, these are all things you can integrate, right? And they're very tiny. 1/2 rho dv1 v1 squared, and you look at the energy on the other half, it's 1/2 dm2 v2 squared, is 1/2 rho dv1 v2 squared. And again, we can add these, right? So we add them, we get, well actually here I'm gonna take the difference. Am I gonna take the difference? Yeah, I'm gonna take the difference. The change in kinetic energy from 0.1 to 0.2. So dk2 minus dk1 equals to 1/2 rho dv2 v2 squared minus 1/2 rho v1 squared.
But then V is just not tiny.
Okay. And then from here, depending on what it is, I can factor out dV. So
And
if
what
it's
is V?
incompressible, then dk equals 1/2 rho dV v2 squared minus v1 squared.
Professor, why is one of them VV and then one D just V? Is like V just V2 just bigger than DV?
Where? Here?
Yeah, it says it's DV V squared, so it's just DV smaller than V?
Okay, I understand my notes now. I understand my notes. I know why I put this here. This is volume. This is velocity. Okay, velocity. So now you understand why I always put the bars and the arrow on top and I'm very anal about it. That's because you get mess ups like this and people get mad and everyone's like, what do you do put this there? It's like, okay.
You'll be fine.
Alright, so du equals rho dv g y2 y1. Can you guess how I just wrote that down, right? Rho dv, that's just my mass, so this is just mg, right? mg, and then y2 minus y1 is just, comes from here, so I just define this as y1, right? And then this here as y2. So that's the change in gravitational energy. And now we're going to do what we've always done, right? And it's just add up all the different energies. So let's add them all up. So we have total work equals kinetic plus potential, right? And so we have P1 minus P2 times dV. I'm going to do this for an incompressible fluid.
Moment, right?
And then we have 1 half
That's
rho
pressure, right?
dV V2 squared. And I'm going to drop the arrow now that I've converted this back into just a regular, same volume for everybody. V1 squared plus rho dVg y2 minus y1.
D.
And then we have these dVs everywhere, right? So we can cross out the dVs. And we're left with P1 minus P2 equals 1 half rho V2 minus D1
Yes, pressure, yeah.
plus rho G Y2. This is called Bernoulli's equation.
Oh, and P stands for pressure, right?
Yeah. So this is pressure. So this is change in pressure. This is just sort of your kinetic energy change, right? If you have volume here. And then this is your gravitational change. Bernoulli's equation you will use a lot if you do anything in fluids or mechanics with fluids. Any kind of plumbing, any kind of anything you can imagine with the fluid. Bernoulli's equation is the foundation for it. I'll do examples next class. Well, we have an exam next class. After next class, I'll do some examples. They're a little bit long.
Really like this concept.
Yeah, that's it.
It was really fun. It was really fun once it clicked. Oh.